Welcome to this session on the design and analysis of algorithms. Today, we will be diving into a fundamental topic in theoretical computer science, the Clique decision problem and its relationship to Cook's theorem. In the context of the design and analysis of algorithms, let's define what a clique is and why it matters in graph theory. First, what is a clique? A clique is defined as a group of vertices within an undirected graph where every vertex is connected to every other vertex. In simpler terms, you can think of it as a fully connected group where a direct link exists between every single member of the set. Second, why do we use cliques? We use the concept of cliques for several analytical purposes. To find strongly connected groups within a larger data set. To identify complete relationships that exist within a network. And to analyze complex graphs by looking for these specifically tightly linked structures. Understanding these structures is the first step toward solving more complex decision problems in algorithmic theory. Let's look at a step-by-step example of the clique problem. Step 1 is to understand the structure. As we mentioned, a clique is a set of vertices where every pair is connected by an edge. If you look at the graph on the right, you can see vertices A, B, and C. Because A connects to B, B connects to C, and C connects back to A, they form a fully connected group. Vertex D, however, only connects to B, so it isn't part of that specific clique. Step 2 involves our given input. In a standard clique decision problem, we are provided with two things, a graph, denoted as $G, V, E, $, and an integer $K, which represents the target size of the clique. Our goal is simple to state but difficult to solve. We must check whether there exists a clique of size $K within that graph. Let's walk through a concrete example using the graph on your screen. Step 3 is to identify our example graph. This graph contains 4 vertices, A, B, C, and D. The edges connecting them are A to B, A to C, B to C, and B to D. Step 4 is to choose our target size, $K. For this example, let's set $K is equal to $3. This means we must check if any 3 vertices form a fully connected subgraph. Finally, in step 5, we select a set of vertices to test. If we try the set A, B, C, we can see that A is connected to B, B is connected to C, and A is connected to C. Since all pairs in this set are connected, we have successfully found a clique of size 3. Step 6 is to verify all pairwise connections. We check the edges between the selected vertices. First, edge A to B exists. Next, edge A to C exists. Then, edge B to C also exists. Since all required edges are present, all pairwise connections are verified. Now moving to step 7, the decision step. Since all the selected vertices are mutually connected, the set A, B, and C forms a 3 clique. Therefore, the answer is accepted yes. In step 8, we try a larger value of K, which is K equal to 4. We consider the set A, B, C, and D. This set is not a clique because the edges A to D and C to D are missing. Hence, the result is rejected, no. Now let us look at the applications of the clique problem. First, in social networks. Cliques are used to find close friend groups where everyone knows each other. Second, in bioinformatics. Clique detection helps in identifying interacting proteins or genes. Third, in communication networks. Cliques are used to identify fully connected subnetworks. Fourth, in pattern recognition. Cliques help in grouping highly similar data items. Finally, in market analysis, cliques are used to find customers who share mutual interests. These applications show the importance of clique problems in real-world scenarios. Now let us understand Cook's theorem. Cook's theorem states that the Boolean satisfiability problem, also known as SAT, is NP-complete. This means that every problem in the class NP can be reduced to the SAT problem in polynomial time. Next, let us see why Cook's theorem is important. Cook's theorem is important because it introduced the first NP-complete problem. It provides a strong foundation for proving that other problems are NP-complete. It also helps in understanding the relationship between the complexity classes P, NP, NP-hard, and NP-complete. Therefore, Cook's theorem plays a crucial role in the study of computational complexity. Now let us understand a step-by-step example of Cook's theorem using the SAT problem. Step 1 is to understand Cook's theorem. Cook's theorem states that the Boolean satisfiability problem, also called SAT, is NP-complete. This means two important things. First, SAT belongs to the class NP. Second, every problem in NP can be reduced to the SAT problem in polynomial time. Now moving to step 2, the given SAT formula. The given Boolean formula is open bracket A or B close bracket and open bracket not A or C close bracket. This formula will be used to check satisfiability in the next steps. Now let us move to step 3, which is the non-deterministic guess, also called the assignment step. The algorithm guesses a truth assignment for the variables. Variable A is assigned false. Variable B is assigned true. Variable C is assigned true. Next is step 4, verifying clause 1. Clause 1 is A or B. Substituting the values. False or true evaluates to true. So, clause 1 is satisfied. Now let us verify clause 2 in step 5. Clause 2 is not A or C. Since A is false, not A becomes true. True or true evaluates to true. So, clause 2 is also satisfied. Now let us move to step 6, the final evaluation. Both clause 1 and clause 2 evaluated to true. Therefore, true and true results in true. Next is step 7, the decision step. All clauses evaluate to true. Hence, the given Boolean formula is satisfiable. Therefore, the SAT problem accepts this input. Finally, let us conclude. The SAT problem has a valid truth assignment. This confirms that SAT belongs to the class NP. By Cook's theorem, the SAT problem is NP-complete. This completes the step-by-step example of Cook's theorem. Applications of Cook's theorem. 1. Proving NP-completeness. Used to prove problems like clique, vertex cover, Hamiltonian cycle. 2. Algorithm analysis. Helps identify problems unlikely to have polynomial time solutions. 3. Optimization problems. Guides use of heuristics and approximation algorithms. 4. Theoretical computer science. Forms the basis of computational complexity theory. Now let us understand the relationship between the clique problem and Cook's theorem. There is a direct theoretical relationship between the clique decision problem and Cook's theorem in computational complexity. First, let us look at Cook's theorem, which is the base result. Cook's theorem states that the Boolean satisfiability problem, also known as SAT, is NP-complete. This means that every problem in the class NP can be reduced to the SAT problem in polynomial time. Because of this result, SAT becomes the starting point for proving many other problems as NP-complete including the Clique problem. This establishes a strong connection between the Clique decision problem and Cook's theorem. How Clique is related to Cook's theorem? The Clique decision problem is proved to be NP-complete using Cook's theorem indirectly. Now, let's look at the logical chain. First, Cook's theorem establishes that the Boolean satisfiability problem, also known as SAT, is NP-complete. Next, there exists a polynomial time reduction from SAT to Clique. This means that any instance of SAT can be transformed into an equivalent instance of the Clique problem in polynomial time. Because SAT is NP-complete and SAT reduces to Clique, it follows that Clique is also NP-complete. This logical sequence explains how the Clique problem's NP-completeness is derived using Cook's theorem. Explanation in simple words. Cook's theorem gives us the first NP-complete problem, which is called SAT. To show that Clique is NP-complete, we do two main things. First, we show that Clique belongs to NP, which means that once we are given a solution, it is easy to verify. Second, we reduce SAT to Clique in polynomial time. Since SAT is already known to be NP-complete, this reduction proves that Clique is also NP-complete. Now, let's look at a small illustrative idea of the SAT to Clique reduction. Each clause in SAT is represented as a group of vertices in a graph. Each vertex represents a literal from the clause. An edge is added between vertices if the literals are compatible, meaning they do not contradict each other. A K-clique in the graph represents a satisfying assignment that picks one literal from each clause. So, if a clique of size K exists, then the SAT formula is satisfiable. Why this relationship matters? This relationship shows that the Clique problem is as hard as SAT. It allows us to classify Clique as an NP-complete problem. Because of this reduction, Clique becomes a foundation for proving many other problems NP-complete. In short, understanding this relationship helps us understand problem hardness and how complexity results are built in computer science. Thank you for your attention.